The mole is an important component of chemistry. It is the common currency chemists use to describe chemical reaction. It is the standard unit for describing the amount of a substance. The mole is equal to 6.02 times 10 to the 23. And this is a huge number. It is 602 followed by 21 zeros. To put this in, to give an idea of how big this is, if we had a mole of dollars, that would be enough money to give every man, woman, and child on Earth $86 trillion each. So it's a huge number. Now, even though it's a huge number, because atoms and molecules are so small, the amount or the mass or volume of a mole of a compound is typically surprisingly small. Take liquid water, for example. A mole of water has a volume of 18 milliliters and a mass of 18 grams. So 6.02 times 10 to the 23rd molecules of water has a mass of 18 grams. Now, to see why a mole is important, imagine a question like this. Now, this is a fairly typical question you might get in a basic chemistry situation where we wanted to produce hydrogen gas from water, and we can do this by applying electrical current. So we have a question such as, how much hydrogen gas is produced from the electrolysis of 50 mils of water? So notice we are starting with a volume milliliters, and we have an amount of hydrogen gas we want to be produced. Because it's a gas, it's probably going to be in another volume unit, such as liters. This is an electrolysis setup. If you apply a current through a volume of water and set it up so that any bubbles that form on the wires are trapped, over time the energy from the electricity breaks down the water molecules and you get a volume of hydrogen gas and oxygen gas. So to look at this in a little bit more detail, the energy from the electricity breaks water down into hydrogen and oxygen gas. Now, to do this as a chemical calculation, we need to look at this general formula and set it up so it's ready to do the calculations. The first thing we have to understand is that liquid water starts as liquid and breaks down into hydrogen gas and oxygen gas. So we have a phase change going on here. And secondly, in order to work with this equation, it must be balanced, which means we need the same number of hydrogen and oxygen atoms as water and hydrogen and oxygen atoms as hydrogen and oxygen gas. And in order to do this with this equation, to balance it, we have right now the way it's drawn, we have too many oxygen molecules, so we need more water. So 2 moles of liquid water break down into 2 moles of hydrogen and 1 mole of oxygen gas. So set up this way, the equation is balanced. I didn't want to do too much calculations in this presentation, but it's a good example of how you kind of can't get away from math when you're dealing with these kind of things. Even to illustrate the point, we need to do a problem. So I'm going to work through this quickly. If I go too fast, you can go ahead and pause and rewind this as needed. But here are the assumptions. We're going to assume we're working under standard pressure and temperature, which is 1 atmosphere and 273 Kelvin. Under these conditions, as we said before, a mole of water has a volume of 18 mils. And more importantly, it has a mass of 18 grams. Now, the mass of a mole of a compound is its formula weight. I'm not going to go through the calculation here, but there is another YouTube video showing how to calculate the formula weight of a compound. So you can check that out if you want help with formula weights. The other thing we need to know is that a mole of a gas has a standard volume. That volume is 22.4 liters. So that's just a given. If we have a mole of gas, we can convert to a volume of gas by this 22.4 liters per mole conversion factor. So with all of this and the balance equation, which is 2 water molecules produce 2 hydrogen and 1 oxygen molecule, since we want to go from water to hydrogen, what's important to notice once this equation is balanced is that for every water molecule, we end up with a hydrogen molecule. We start with milliliters of water, and we want to go to grams of water to get to its formula weight. And that's just using the density of water as a conversion factor. So 50 mils of water times its density, 1 gram per milliliter. The milliliters cancel, and we end up with 50 grams of water. Now, this 50 grams of water is the formula weight of water. So we can say 1 mole of water has a mass of 18 grams. To convert to moles, 50 divided by 18 equals 2.78 moles. So now we are in moles of water. We now need to convert from moles of water to moles of hydrogen gas, the compound we're interested in. And since we said earlier 1 mole of water produces 1 mole of hydrogen gas, to convert moles of water to moles of hydrogen gas, we just say it's the same amount. So now we have moles of hydrogen gas, but we want to get out to a more meaningful unit for us, which in this case is volume. So we use the 22.4 liters per mole to convert moles to liters. Just one final conversion factor, 2.78 times 22.4. The moles cancel, and we end up with 62.3 liters of hydrogen gas. I went through that quickly, and the specifics of that particular calculation aren't as important as just understanding the general flow, because it is a common template for many calculations. The important thing to see is that we see the world in terms of tangible units such as volumes in milliliters or liters, or masses in grams, or weights in newtons. But chemistry occurs at the level of actual particles of a substance. So we need to bridge this gap. And the mole is the standard unit that we use to bridge this gap. So while it is a convenience, it is more than just a convenience. And that water electrolysis calculation illustrated how the mole is typically used. To do it generally with a chemical problem such as the one we solved just now, where we start with a meaningful unit to us, such as grams or milliliters. And in order to figure out what's going on at the chemical level, we need to convert that to moles, do whatever calculation we need. In this case, we got from water to hydrogen. And then once we have our answer in moles, typically we want to go back out to our target unit that has more meaning to us. In this case, we went back out to liters. And this is a very common workflow when performing calculations in chemistry. We go from units we can measure through the mole back out to units we can measure.